Okay, hello everyone. I think everybody is in almost, yeah. Okay, hello again. Welcome to our Young Women for OR webinar. This is the second this year. So it's going to be on location analysis. My name is Dilek Günlich. I'm the secretary of the Wisdom Event Subcommittee. Just a reminder that this meeting is being recorded and it will be posted on our YouTube page. Okay, so okay, so just to give you a brief idea about our forum, which we do as we start the webinars. So Wisdom aims to provide a platform to support the participation of all genders in the in OR. Okay, we would like to advise or make recommendations on especially that on issues that women face in our area. We would like to promote championing and networking and mentoring. We have we want to promote a conversation around how OR can be utilized for a more diverse and inclusive future. We will have actually a EDI policy on the Euro website as well. For that, we do these webinars for the young women in OR. We have meetings at the Euro conference, the annual conference, and so we have a lot of different activities, mentoring activities as well. So please keep following us. So Young Women for OR is one of the activities that we do. So every year we select 12 young women that study operations research topics. And here you see the awardees for this year. So over the year, we have 4 webinars where in each webinar, we have 3 of these speakers presenting their research. And then we have one subject matter expert that within the webinar that helps us to understand these research areas better. So today, as I said before, our topic is location analysis. So we have the speakers, Marta Baldomero Naranjo, Concepcion Dominguez, and Serena Figuero. And our subject matter expert is Bahar Yetişkara from Bilkent University in Turkey. Her research interests include distribution logistics, humanitarian logistics, hub location. She has a very large number of papers, very accomplished, and we are very excited and happy that she's joining us today. So with that, I don't want to take any more time. I will come to the events at the end. So I would like to give the floor to Marta for her presentation. Okay. Okay, so we have 10 minutes for each speaker, and we're going to have the questions at the very end. So after each speaker presents, then we're going to move on to the subject matter expert for her comments and questions. And then we are going to have time for questions and chatting and networking, if you like. So Marta, thank you so much. The floor is yours.
Thanks for the presentation. Okay, can you hear me? Okay, yes. Well, I'm going to present a work entitled Accrediting Age in the Massima Coverage Location Problem. It is a joint work with George Katsik, Alfredo Marin, and Antonio Rodriguez Chia. Well, I'm going to divide my presentation in 4 main parts. First, I'm going to introduce the topic. After that, I'm going to present some ideas of the formulation that we proposed. Then I'm going to comment the computational experiment. And finally, I'm going to present our conclusion. So, as probably many of you know, the maximal coverage location problem aims to locate P facilities in order to maximize the cover demand. The idea of this problem is that a client is going to consider to be covered if the distance between the client and the facility is lower than or equal to a given coverage radius. This problem was introduced in this paper some years ago. If you see that in a graphical representation, for example, if this is a graph where the number represents the distance between the nodes. And we assume that all the clients demand one unit. If we want to locate one facility, the optimal location is going to be the red point, and all these orange points are going to consider as cover. What we propose in this paper is that we are going to be able also not only to locate the facility, but also to modify some parameters of the network. In fact, we are going to propose that we can reduce the length of some edges. That has many applications, as in the public government, that can improve some roads in order to reduce the travel times, or even in shopping center, airport, train station, that you can't locate a passenger conveyor or escalators in order to reduce the travel time in our network. So the idea that we proposed is that do this process, these two processes simultaneously. That is, decide where to locate the facility, and also having a budget, decide which edge we want to improve or upgrade in order to reduce this travel time. We also assume that we have a cost per unit of reduction, and we have a maximum reduction per edge. So if we saw that graphically, we have these fast roads here, and here we have a path that you can traverse it. You traverse it slowly. You can decide to invest a little bit in order to improve a little bit this edge, or improve the maximum amount here so you can go faster. That is the idea of our problem, and at the same time we locate these two facilities, and this facility are the ones that are going to be, these are the clients that are going to be covered. So if we saw that in the sample that we saw before, we have this situation with no upgrading. If we have a small budget, the location of the facility changes. The optimal decision is to upgrade the two edges, and we cover more demand. Again, if we increase our budget, again, the optimal location of the facility changes, and also we cover more demand. What we also prove is that if both processes are done simultaneously, the optimal solution improves that with respect to if we do this process in two steps. That is, if we locate the facility and then improve the network, the solution that we obtain is worse. So is justify using this model. What we propose are three different formulations. The first formulation use one family of constraints that is what we call the flow variables. The idea of this variable is that we, for each pair of vertices of node of the network, we save which arcs traverse each path from the client to the service facility. And also we have another family, the Y variable, that are the classical covering variable that indicate with this for each client, which is the facility that is assigned to this client. The other, here is the formulation, but I'm going to skip all the details due to the time constraint. The second formulation that we propose is based on the idea that we are not going to save all the information of the path, only the next one. That is, for example, is the node L is covered by F, I'm not going to save as before all the arcs that traverse this path. I'm only going to save that the next node in his path to the facility is J. That is, I only know who is the next node in our path. I'm not going to save more information. And the third family of formulation use this idea of knowing who is the next node in my path and also discovering variable. So the idea is I know the next node and also the final node, who is going to be or where is going to be the facility that is covering my client. So with these three formulations, what we do is to develop some theoretical properties that allow us to prove that the integrality condition of some family of variables can be relaxed. Also, we develop a pre-processing, and I'm going to explain the main ideas. The idea is that if two nodes, the distance between two nodes is lower than or equal to the coverage radius, we don't need to compute or we don't need to look for the best path, because or even to check if after the grading the distance between both nodes is lower than the coverage radius. We know that if we locate one facility in one node, we are going to cover the other one. And on the other way around, the same. If we know that the distance between two nodes is greater than the coverage radius, even reducing the maximum amount allowed in all the edges, or even expending all the budget, we know that it is impossible that if we locate one facility in one of these vertices, the other is going to be covered. What we propose is several procedures to find a balance between accuracy and computational time. Moreover, we develop some family of valid inequality. We adapt the close assignment constraint or some ideas, because we cannot apply that exactly to this formulation. We strengthen several families of constraints. We also propose valid inequality of exponential cardinality, and we develop a separation procedure in order to find the better one or the best one in the branch bound and cut process. What we prove all of that in a computer with this characteristic using simplex. And what we check was the complete graph and also the PMET graph that are sparser one. And we check all these different parameters. Well, we also check regarding the valid inequality, different ideas, that is including them initially in the formulation or in a pool of user cut, or using even user cut callback from simplex. Well, what we obtain here, we represent the average time of each of the formulations, and without and with preprocessing. These two represent with using preprocessing, and this one without preprocessing. What we obtain is that the average time is much smaller if we use the preprocessing. And for path, we cannot use it, but we prove that it's really useful using that. Moreover, we test all this formulation with the valid inequality. We compare this other formulation. In the complete graph, we obtain similar result with all of them, but it's better to use the valid inequalities. Finally, in the sparser graph, we see that the formulation that only saves the information of the next node and the final node provide much better result. And again, using the valid inequality is really interesting. That's all. Well, we present Remix integral formulation. All the detail can be found in this paper, and we have many ideas for future work regarding this problem that maybe we can comment later in the question part. Thank you for your attention.
Thank you so much, Berta, for this very nice presentation. Next, we can move to Concepcion's presentation. You're on mute, okay.
Okay,
Can we make it into presentation mode?
sure. There we have it.
Thank you.
Just give me 1 sec so that I can move this and see my own presentation. Okay, so thank you very much for joining. And I'm going to talk about the cooperative maximum capture facility location problem. And this is a working collaboration with Ricardo Vázquez, Juan Miguel Morales, and Salvador Pineda from the OASIS Research Group here in the University of Madrid. So, sorry. Okay. So in this work, we're going to generalize the well-known maximum capture facility location that was just introduced by Martha. So in this case, we have a company which is interested in opening a certain plants in order to maximize the customer capture with regard to a competitor firm which already operates in the market, which in this case is represented by this blue dot in the middle of the figure. And the customers can be modeled using different rules, but the one that we generalize is the binary rule, which is also known as the utility maximization rule, where essentially each customer assigns a utility to each of the open plants. And so once the plants are open, they will patronize their favorite open plant. So we don't split the demand, either it goes entirely to the competitor or to our firm. In this setting, we have opened 2 different plants in 2 different locations. And in doing so, we have captured 3 of the customer classes out of the 5 that were available. So in the generalization that we tackle, on top of sticking with this binary decision rule, we consider a cooperative setting. In this sense, we no longer have a utility that is given in terms of just one facility, but the capture utility is given in terms of an aggregation of the partial utilities of all the open facilities. So the customer will most likely patronize different facilities, but all of them from the same company. So customers are, in a sense, loyal to the company. And we find different applications for this setting. The first one, which is the one that drew our attention to this problem, is an application where we consider that we capture a customer when he buys a specific product. In this case, the product is the electric vehicle. So in this sense, when a customer purchases an electric vehicle, he no longer patronizes the oil stations, but he moves to charging stations for electric vehicles. So due to the European Green Deal, the adoption of electric vehicles is due to increase exponentially in the following years. So this is a problem of interest nowadays. And from the point of view of a government, it might be interesting to decide on the locations of electric vehicles charging stations, so as to increase this adoption of vehicles. In other applications, we might be dealing with customers that are captured when they pay a membership for a service. So this is the business model of a company, a gym company well known here, which is called Basic Fit, where basically you pay a monthly fee, and in exchange for that, you are allowed to visit any of the gyms available from the company, even from different countries. So the way that we decided to model this capture utility was by means of an ordered median function. And this function assigns importance weights to the sorted partial utilities and then aggregates the weighted utilities. So down at the bottom of the slide, you can see a small example. We have weight vector lambda, which is 1, 2, 3, and the partial utilities of three locations for plants. 2 of them are open and the 3rd one is not. So the capture utility in this setting would consist of, first of all, ordering the utilities from the largest to the smallest one, so 7, 3, and 0, and then multiplying each utility by the corresponding lambda weights. So the total capture utility in this case would be equal to 13. So as I will intend to convey here, this cooperative framework with this way of modeling the capture utility suits many different approaches depending on the weights that we choose. So for instance, the non-cooperative approach can also be covered if we consider a lambda equal to 1 and the rest equal to 0. So this would be the standard utility maximization. And if we move back to the first example that I introduced, and we consider the green customer, this customer has an opt-out utility of 3.5 and is not captured in a non-cooperative setting. So if we consider the small plant, the utility will be equal to 2.2. If we also open a big plant, this utility would increase up to 3, but still the customer is not covered. But if we consider both plants in a cooperative setting with the lambda weight that it's in the screen, then we have that the utility increases up to 4.4 and this customer is captured. So from the literature, we already know that we can model the order median function by means of an assignment problem. So we have the sigma variables, which are the assignment variables from a given customer I, they move in the indexes J of the plants and R from the indexes. So this variable is equal to 1 if in location J there is a plant that gives the RF largest utilities for the customer. Then we have the standard constraints of the assignment problem and some nonlinear constraints that make sure that the utilities are ordered from the largest to the smallest one. But what turns out is that for the cases that we study and we're most interested about, which is assuming a non-increasing vector, then we have, that these constraints don't need to be added to the formulation. So we can model this problem by choosing a linear assignment problem. As for the first formulation that we derived for this problem, it has a bi-level structure where in the first level, we have a company designing on the locations of plants. So xjk will be equal to 1 if a facility of type K is installed at location J. We have also indices for time period T and scenario S because we consider a stochastic framework. Then on the second level, we have customers, which are maximizing the utility, the capture utility. So in this case, the binary variables Zi will be equal to 1 if the customer I is captured in the corresponding time period and scenario. Then we have the continuous constraints, the continuous variables, that model the partial utilities. And finally, the embedded assignment problem that we need in order to model the capture utility for each customer. The bi-level problem has this structure, the formulation, where these constraints model the location of the plants. So we can only establish one plant of any type at each location. When we install it in a time period, we're allowed to upgrade it, but we cannot downsize it or remove it in subsequent periods. And then we're assigned a budget for each time period, and we have to comply with it. Then we have the partial utilities, which are given in terms of the type of plant that we install and the location, the distance, the size, and certain parameters. And finally, we have the second level problem, which is the maximization of the utility between the opt-out utility, which is a parameter, and the capture utility, which is this assignment problem that is embedded here. Finally, in the objective, we're just maximizing the captured demand. So from this bi-level setting, we derived certain exact resolution approaches to solve this problem, and we conducted a case study in the city, taking instances from the city of Trois-Rivières in Quebec, in Canada. And what I wanted to point out here is not only that obviously changing the lambda weights of the modelization of the captured utility is going to have an impact on the number of customers that are captured in an optimal solution, but that it also affects the final locations of the plants. So here, if we consider the non-cooperative setting, this picture A, with respect to picture B, which is the cooperative setting, we have that, first of all, one of the plants, which is in yellow, the smallest one at the right, wasn't open, and then the size of the plants significantly differs between one setting and the other. So it might be interested to study to make sure that we model the customers in the correct way when choosing a cooperative framework, or even to robustify the solutions with respect to some uncertainty in these weights that we might have towards the customers. And thank you very much for your attention.
Thank you, Concepcion. Very nice presentation and very good timing for both the speakers. Now, Serena, can we have your presentation next?
Can you see the screen? Okay. So, hello everyone, and let me thank the Zero Wisdom Forum for giving us the opportunity to present our research. With this talk, we'll introduce a novel class of multi-objective covering location problems. This is a joint work with my colleague Antonino Scalambro from Sheffield University Management School. With our research, we had several aims because we wanted to extend the applicability of covering location models by accounting for specific requirements which may arise from administrative, managerial, and operational needs. We also wanted to address all those spatial-related requirements which may arise when the set of candidates is clustered in regions or zones. And we also wanted to integrate advanced connectivity features and measures within classic covering location problems. These ideas came from an analysis of the related literature where we found several gaps, and so we tried to devise tools and methods to fill those gaps. Specifically, we jointly considered, zonal requirements and network connections. Also, we accounted for structural, economic, and operational aspects of connectivity features in covering location, and we introduced measures to contain the maximal distance between any located facility and a special facility that I will call the route for the moment. And finally, we included the possibility to choose the route facility within the decision-making process. So in this way, we came up with a multi-objective covering location problem with zonal requirements and the shortest path tree of active facilities, where we have connectivity setup cost among the objective functions and novel criteria to appraise the quality of interconnections. In order to move to the formal description of this problem, I think we need to focus on the concept of route. As I told you before, a route is a special facility that is tasked to serve as a depot for active facilities or to feed them as a distribution center. And we suppose that each active facility can act as a route. Also, in our problem, we assume that the reference area is partitioned in zones and that the connectivity setup function verifies the triangular inequality. So in our problem, we have that several decisions need to be made concurrently because we want to select exactly one facility to locate within each zone. Among those located facilities, we want to choose the route facility, and we also want to identify a shortest path tree connecting the active facilities with the route. And while making these decisions, we want to pursue different and conflicting goals because we want to maximize the cover demand. We want to minimize the overall service network setup cost, and we want to minimize the maximum length of any path from the route. So the resulting problem is a multi-objective problem for which we also prove the NP-hardness. And to obtain a mathematical formulation for this problem, we devised an MIP formulation which leverages the use of both binary and continuous variables to define the connection. Also, in the setup cost function, we included both the cost to define the connections and the cost related to the activation of facilities. And now I want to show you how the solution for this problem looks like. Here we have an area that is divided in 5 zones. The triangles denote the facility sites and the circles are the demand nodes. You can see that we have one active facility within each zone and that the route, that is the red triangle, is connected with all the remaining facilities with a tree. As I told you, anyway, this problem is multi-objective, which means that if we want to support the decision-making process, we need to provide a representation of the relevant Pareto sets. And at this purpose, we adopted at first an exact approach consisting in the adaptation of the robust version of the AlgMecon framework. Basically, AlgMecon is a generation method that iteratively solves a single objective problem obtained from the original problem. And in the robust version, we have that bypass coefficients are used to improve the percentage of single objective problems that are not solved because they are either repeated or unfeasible. In particular, what happens is that these problems are solved with a solver, which means that if the size of the distance becomes too high, then the resolution with the solver might be impractical. That's why a heuristic procedure would be more useful. And at this purpose, what we did was developing a math heuristic approach which leverages on a mathematical property of our problem. In fact, we observed that the network of facilities is a metric graph, and this means that we can find a shortest path tree by considering the star graph centered in the root node. So in our math heuristic, we have that once we have solved the continuous relaxation of the max covering location problem with zonal constraints, at each iteration of the AlgMecon framework, we fix a set of facilities with a pseudo-randomized rounding procedure, and then we compute all the possible star graphs and check for the feasibility and dominance of the resulting solution. In particular, we devised a set of experiments in order to obtain a proof of concept for our model and also to appraise the scalability of the proposed solution approach. The solution methods were implemented in Python, and the experiments were run on two sets of benchmark instances that were adapted from the literature on cluster problems and p-medium problems. From those experiments, we obtained several interesting takeaways because we found that when we have an elevated zone density, both in terms of candidates and demand nodes, then a greater computational effort is needed to solve the problem. On the other hand, if we have zone sparsity, then the advanced network connectivity features became more challenging. And in general, we observed that according to the specific zone topology, the fulfillment of all the objectives may be rather complicated. Anyway, up to now, I presented a situation in which we only have to locate one route. But if we think about realistic scenarios or anyway large size distances characterized by a lot of facilities and a lot of zones, then in this case, it might be more useful to have more than one route. So we asked ourselves, what happens if we have more routes? And we realized that in this case, we need to switch from the shortest path tree of active facilities to a shortest path forest of active facilities. From a mathematical standpoint, this means that we need to update the connection variables, the setup and path length function, and of course, the route selection constraints. And I want to show you how a solution can be seen. It can be if we assume that R is equal to 2. So again, we have an instance with 5 zones. And in this case, you see that we have 2 routes, so 2 red triangles, which are connected each with a different subset of facilities. So the resulting solution comprises now 2 trees. Anyway, we're still working with a multi-objective problem, which means that we can still adapt the AlgMecon framework, but once again, as the size of the distances increases, then it is impractical to use the solver for the single objective problem resolution. And this is true also if the number of routes increases. So also in this case, we develop a math heuristic procedure, which once the set of possible routes has been obtained, as I explained before with continuous relaxation, we have that this procedure computes a forest by assigning each non-root facility to the closest route. And then if the resulting forest is unfeasible because there is at least an isolated route, then the procedure evaluates all the possible switches between a non-root facility and the isolated route, and it performs a switch whenever we have the smallest contribution for either the setup or the path length function. Once again, we test our methods on the same set of benchmark instances and considering different configurations for the number of routes. Those experiments confirmed the accuracy of the model and also its functionality in providing either an exact or an approximate design for facility location and connection. Also, from those experiments, we found that when we have to locate only one route, then we have to prefer the first formulation I showed you before. And also we found that the matheuristic approach is able to boost the scalability of the solution method. As regards the number of routes, we also found that if we increase the number of routes, then the advanced connectivity features are computationally more challenging, even if from a managerial point of view, if we allow for the installation of more routes, we are able to obtain more cost-effective configurations. And basically, this ends my presentation. I just want to add that this work was presented exactly 1 year ago at the Kyoto Summer Institute on Location Science, and that the resulting paper has been accepted on the related special issue that is going to appear on Computers and Operations Research. And that's all. Thank you for your attention.
Thank you, Serena. Very nice presentation. Now, so we have completed all the speakers. Next, we are going to have our expert, Bahar Yetishkara, for 10-15 minutes for her comments and questions for the speakers.
Yeah, first of all, stop saying expert, because especially with these young, brilliant ladies, they're all experts. Everybody's expert in their own field. So it's so nice to be here. It really feels nice to be a part of this group. And I'm really thrilled to see all these brilliant young ladies explaining very nice topics about location. And being a location person myself, I really like it. So congrats to all of you, first of all. I enjoyed all the talks, and I did take notes, but I was trying to take notes for potential questions, and then a couple of slides later, they answer my questions. So it's really, really very nice. I still want to maybe put more emphasis on certain points, I mean, just for the general audience, if not everybody might not get everything that you said. So just to be on the same page, I'll start with Marta, right? She did talk about this maximum covering location problem. I loved the problem as most of it. So I mean, I really like the idea that you're locating a facility, and then in the meantime, you're also locating certain arcs, to choosing certain arcs, which is another location decision, to put some emphasis on so that they can shrink and the distance can be less so that more people can be covered, which is a great idea. You do have your own agenda. I have seen that in your future research topics, but I would, for example, I mean, if this was, if you were my student, I would like to continue, for example, like this is, since you're locating facilities and you're locating arcs, this does look like hub arc location problem that James, well, hub location plus certain, you may link if you wanna, because now if you decide that those are your hub arcs, then you actually discount the travel time on that hub arc, which is similar, but in that case, you're giving, so in your solution, the OD, there is no OD, the service is at the facility, whereas in the hub case, the origin and destination are far apart, but that may lead to an additional venue for you if you would like to continue. And I also think that you may consider, like, you're using complete network, but once you shorten an age, it may appear in more than one path. If you're, if especially like in Canada, the road network definitely is not complete. So for certain, I mean, utilizing the physical infrastructure, because as far as I know, you assumed complete network, no?
We check both kinds of
okay.
graph. We check the complete one and the other more sparse.
Because even though it may be more costly, if an arc appears in many paths, it may be more beneficial to invest in an arc. So it may be different. It was my question, but if you have
Yes, it's more difficult to solve the
of course, challenge
obviously.
for your own students, not for you.
Yeah.
And again, one additional tiny little thing, like if the arc that you're investing is also connected to the facility that you're locating, maybe the cost can be different. Just another spin-off can be, because I don't know, because in your scenario, there is no relation between the arc that you're investing in and the location facility that you're locating. But there may be, I mean, you may have different ways of costings. I don't know, just a spin-off if you want
It's a nice suggestion. Yes, we can think about that, and also how it can be related with the hubs that you propose at first. Thank you for your comments.
You're welcome. Thank you for your presentation. Concepcion, am I saying your name correctly? I keep writing it how do you spell it. Am I correct?
Yes, it's perfect. Concepción,
Okay.
yes.
Okay. In your scenario, this cooperative capture thingy. For a while, I was writing bi-level, and then you popped the formulation as bi-level. So yes, definitely your model is bi-level, and which is a challenge in solving. So normally you should have struggled a little bit in those either containers, or I don't know how you solved it, but apparently you did a good job. So okay, I mean, linearizing bi-level formulation is a challenge in itself. That's why I was like, this is bi-level, how can she? But then you did it as well.
Yes, but in this setting, it was a particular setting where you only deal with two different like capturing decisions, because you consider the global capture of the customer, including on all the locations. You only have one variable per customer, and obviously the problem is separable by customers because we didn't consider any capacity. So in this setting, it was not difficult to derive a
Linear version.
Single level problem from the bi-level setting. And we also have the embedded assignment problem, but again, this could with some tricks it could be also removed, and it could go straight up to the single level problem.
Okay, yeah, that is true. Yeah, I mean, for spin-offs, I mean, I'm not that rich in your scenario for the spin-offs, but of course, different utility functions can be, but you also said that, and it's not an easy thing to come up with a utility function that could be solved. I was thinking, I mean, since my heart is currently in humanitarian applications, but for everybody I'm listening, I was thinking, how can I put this into my disaster domain? Of course, I mean, when you're giving public service, so yes, it goes to disaster domain, but for the utility, for example, if it is a volunteer thingy, maybe you may come up with a little bit challenging and fancier approach from the customers. I mean, you're assuming that it's a Starbucks and I'm gonna go and buy it, right? The customers are gonna go based on utility. But if it is like, I don't know, if it's something that you want them to come to you, like if it's a vaccination, for example, something like that, then the top level manager might have different performance metrics, which may lead to additional spin-offs for your problem. I don't know, just a hunch.
Yes, it might be interesting to consider some applications like this. I would probably consider applications where you have to visit the centers, or people have sent from centers in different time periods, because this is when it makes sense to consider several centers at the same time. But yes, why not? And this is an interesting topic.
I mean, you can even compare, like if people want to come, or if you, I mean, in the other case, the government, because your top level manager is the decision maker, you may want to go closer, or I don't know, give something else, establish one more facility. You can actually see what happens between those. Just that could be a spin-off. Serena, you were the last. I liked, of course, I like all of them. I liked all the problems too. I really loved that you're zoning and you're having your trees and everything. And then again, in your scenario, my note was why there is only one route, and then you opened that you're going to open more routes, which is, as I said, these young ladies are so brilliant, very difficult for me to ask questions. When you have more than one route, how about connecting them also? I mean, your forests are standalone, no?
Yes, I have different trees that are connected only with the subset of facilities each.
This is definitely a hierarchical location problem, but if you consider it like that, especially from healthcare or again from disaster distribution center application point of view, like zoning works really well because yes, there are zones and you go top down towards the zone. So again, the shortest path makes sense. The forests make sense, but at least at a star level or something, you may want to have connectivity between the roots of different trees, I would say, forests, I would say.
Okay, so it's interesting, yeah.
It may be challenging, I know, but since you're good in solving all these, your heuristic can again work miracles and you may come up with different applications.
Let's see what happens.
Yeah. That's all from my side, Dilek.
Okay, thank you. Thank you so much for your questions and comments. I'm sure they are going to be benefiting from your comments for their future works as well. So I can open the floor to the audience if anyone has any questions or comments that they would like to share. Okay, Dolores is leaving, so had to leave. Okay, were there any other questions or comments from the audience? Okay, then let me continue with our upcoming events. So if I could share my screen. Okay, I think you can see them now. So here are our upcoming events for 2023. We're having a little bit of break during the summertime in terms of the webinars. We have 2 more left that we plan to do, one in September that is on routing and scheduling, and one in November on optimizing for sustainability and fairness. And then, as you may remember, in December's, we have the winter event, where we announced the awardees of the upcoming year and finish off of 2023. We have 2 papers in progress. Sorry, we have 1 white paper and 1. We have some work in progress. As I said, this meeting is being recorded and we are going to upload it on our YouTube page. So at the bottom here, you can see our website. You can join us. We are a group in LinkedIn. You can join us from there. And this is our YouTube address where you can access previous webinars and this one hopefully very soon. So before I finish off, I would like to thank all the speakers and also our panelists, Professor Kara, and all the committee members for organizing this event. So before I finish off, let me quickly look at the chat so I'm not missing anything.